Okay, hello everybody and welcome to our webinar on ComposicaD-ESAComp solution for composite pressure vessel simulation. Today's presentation will be given by Mike Skinner from Seifert and Skinner Associates and by Harri Katajisto from Componeering. My name is Marko Palantra, I'm from Componeering, and I will give just a short introduction to ESAComp and Componeering to start with. During the presentation you all will be muted. During the session you can type in your questions in the chat pane of the GoToMeeting controls window, and towards the end of the session we will turn on your microphones so you can also ask your questions live. To start with, just a short introduction to who we are. So from our side, Componeering, I'm giving the introduction, and then later Mike Skinner will tell about ComposicaD and his company. So ESAComp is a software that, which development was started already in the 1990s, initiated by the European Space Agency. It's a general composites design software meant to replace different in-house tools that were used in the aerospace industry. It's been developed by Componeering, our company. We are based in Helsinki in Finland. We have also some staff in Central Europe, in Germany and France. Our activities focus on ESAComp software, but we do also engineering consulting. The customer base of ESAComp is quite vast. We have customers in more than 30 different countries all over the world. And all different industries using high-performance composites are practically covered today. Of course, because of our background in the aerospace industry, many of our most known customers come from that area. ESAComp covers a lot of starting from basic laminate analysis, classical lamination theory-based analysis, first or shear deformation theory, and so on, focusing on the conceptual and preliminary design of composite laminates, but then going also into structural elements. We have a vast composite materials database as a starting point for design studies, and from ESAComp you can also export your data into and initial designs into FE software, and even come back to ESAComp after the analysis done with the general FE software. Today's topic is related to one of the structural elements, cylindrical shell structures, and this is a special application where we combine ESAComp with ComposicaD filament winding simulation tool. So at this point I will hand it over to Mike Skinner, who will join us from Salt Lake City.
Hello, this is Mike Skinner. I'm in Salt Lake City, very early in the morning here, but hopefully I can muddle through. I've got a cold, so if my voice sounds a little rough, that's why. I'm going to first talk a little bit about our company, Seifert and Skinner Associates. I'm the guy in the hat. We're actually standing. The guy in the red coat is Axel Seifert, my partner. We're actually standing in a wine field in France. This is a picture that was taken when we founded the company. We both have extensive background in filament winding for many years. And our company works in three main business areas. We have what we call optimum CPV, which is our development facilities for developing and designing, prototype testing, and so on, certification of composite pressure vessels. We actually have a laboratory in Belgium where we can produce these parts, test them, and come up with a good finished design. We also produce the ComposicaD software, which is what I'm going to talk about in a bit. ComposicaD is a fairly inclusive package that covers most filament winding. We do pipes, pressure vessels, of course, which is what we're going to focus on. But we also do curved structures like elbows. We have pipe tees. We do things that are called spars, which are non-round geometries, and a couple of other applications for ComposicaD also. And then our other activity is the CPV Symposium. This is an annual symposium devoted to composite pressure vessels. We just finished up the fourth annual one. It was in Salt Lake City this year. It was very good symposium this year. We had some great presentations, our best presentations ever. We're planning the next one for Berlin, Germany, next year in October, the 13th through the 15th of October. And then we also do some other composite development work that is fairly minor part of our business. We have associates all around the world. We actually have 3 offices. We have one in Salt Lake City, Utah, where I am, in Hasselt, Belgium, and in Mar del Plata, Argentina. This is our development facility. We have 2 large winding machines, one single spindle and one 3-spindle machine for doing our development work. We have all the auxiliary equipment that you need to actually build and cure pressure vessels. We have testing equipment for both low pressure and high pressure testing, some environmental testing equipment, and we have ISO 9000 and COP pending. We actually have certified designs for several different types of tanks. We have an LPG tank design, which is a small low pressure tanks, and we have 2 designs for CFG tanks. These are all type 4 cylinders, 80-liter CFG tank and a 710-liter CFG tank, which we think is actually the largest cylinder ever to be certified. Our main associates, we have associated companies around the world that we work with. Componeering in Finland, of course, is one. Composites in China. Sean, I think you were signed up. If you're out there, welcome. And some of our customers, we have customers all around the world. Most of the major cylinder producers use ComposicaD for their development work, as part of the development work. Now we're going to talk about ComposicaD. So ComposicaD is ComposicaD CPV. This is the version that's designed explicitly for composite pressure vessels. We're going to go fairly quickly through the design here and show you how it works, and then we'll turn it over to Harri to do some analysis using ESAComp. So we're going to first look at a pressure vessel. One of the big advantages of ComposicaD is that it's parametric. We enter dimensions or shape for our underlying mandrel, which is usually the outside dimension of our liner, and then everything is based on that liner geometry. And in this particular case, I entered parameters for a liner. This is designed for a 140-liter tank. This has isotensile domes. Typical geometry. One of the more recent features that we put in ComposicaD is a design tool that will allow us to estimate how much material we need for specific burst pressures. This tool is based on netting analysis. It neglects all of the rest, and it looks slowly at the fiber strength. And it's a little more detail than we can go into here, but it gives you a good first approximation of how much material you need in a vessel for the required burst pressures. So in this window, we can put in our operating pressure, desired safety margins, and come up with a desired burst pressure. Look at our fiber to helical, or helical to circ fiber stresses. We typically want our tanks to burst in the circ direction, not in the axial direction, not in the helical direction. We put in our parameters for the materials that we're going to be using, which we can specify. Here we've got two different, we're looking at a T700 epoxy material. We specified two different materials, one for the hoop direction, one for the helical direction. This is typical because of the manufacturing process. With hoop winding, we're typically going to have a little bit wider bandwidth than we have with our helical winding, just because of the geometry and the mechanics of the winding machines. So for each of these materials, we specify how many rovings, our X values, the densities of the materials, costs if we want to, and the bandwidth that we're going to ultimately achieve on our part. And along with those parameters, we can also specify some two parameters that are used in the design, our ultimate fiber tensile stress and the ultimate fiber elongation or strain. These numbers are actually used in the design window if they're supplied. So we've selected our two materials, one for the helical and one for the hoop direction, and then ComposicaD calculates how many plies we need of each type of material. So the helical layer, it's saying we need about 4.6 plies, which of course we can't do, so we're going to be looking at probably 5 plies, and then 15.8 circ layers to contain the pressure that we've specified. And it also calculates our volume based on the information that we supplied. So unpressurized, our tank is 139.8 liters. At operating pressure, it's going to be 142.9 liters of volume. So now we can specify our laminate structure. Again, ComposicaD is parametric, so each one of these layers builds on the previous layer. This laminate sequence would be typical for a CNG type tank. We start with a hoop or circ and differential layer. We put in some helical layers, another circ, some more helical layers, and then finish off with a circ on the outside. There may be other geometries that would work this as well. This is one that this is not an actual tank. This is just something that we're using for demonstration. But once we build this laminate sequence, then we can calculate all of our winding paths. Each one is based on the previous winding path and the buildup of the material that is put onto the part by that particular layer. Now we can look at our cross section. I'm going to expand this so we can see it a bit better. This is just looking at the dome contour of the part, so you can see each layer that we're putting on. The green layers are actually the circ layers, which would be in the cylinder region, is where the buildup's going to be. But we're looking at the helical buildups now, so each blue layer is a helical layer that we put on. So you can see that we're stepping back the helical to keep the buildup around the dome to some reasonable level. Here's the in the cylinder region. Now this is the transition going into the dome from the cylinder. You can see our first circ, the helical layers, our second circ, some more helical layers, and then our third circ of the material that's being put on the part. Now based on this particular laminate sequence, we can calculate the burst pressure again using our netting analysis. And from this, we can decide whether our design is going to be appropriate for the desired burst pressure. So based on the actual buildup that we have in the laminate table, the circs and the angles of the helicals, then ComposicaD will calculate that design burst pressure. So using our design values, we have a circ fiber stress of 3125 megapascal, and helical fiber stress of 2656 megapascal for a stress ratio of 0.85 between those. That's a typical value for these types of tanks. Some people might go a little higher. But like I say, we want the stress to be primarily in the certain differential direction so that the failure mode is in a certain direction. Now we come down, we look at our design pressures, and we say, oh, over 100% of our design pressures. It took me about 2 hours to actually do that, so it came out exactly 100%. But typically, you don't need to be 100%. You're looking for some value that's going to be close to what you want, and then you can, using some of the other analysis tools, so we can tweak those values a little bit. One of the reasons that we're working so much in this area is that we want to minimize the time it takes to do a more in-depth analysis. And of course, the reason for that is to minimize costs for these pressure vessels, especially the larger CNG tanks that can be quite expensive to fabricate and burst. So if your only method of testing your tanks is to make one and burst it, it can get pretty expensive pretty fast. If we can model the performance of those tanks better in our software, then we can do more iterations in a low-cost environment before we actually have to build a tank and test it. Of course, we can't get away from that testing, but we want to try and minimize it because it can be very expensive. And now we have actually have our part. Everything's ready to go. We can export now to ESAComp. I'm just going to mention in passing, we actually we support ESAComp. We have a couple of other FEA tools that we support also. We're trying to support most of the major FEA packages so we can export to them also. I'm going to export now for ESAComp. We'll do a full part, specify our number of segments, direction. And we're just going to save that data. A few seconds to calculate it. And here's our finished part in ESAComp. And now I'm going to pass this over to Harri, who can talk some more about ESAComp, I think.
Thanks, Mike. And so my name is Harri Katajisto. I'm an engineering consultant at Componeering, and I have around 15 years of experience from industrial composite projects. I have a background in mechanics of materials and then lightweight structures, and I'm a member of NAFEM's Composites working group. So now I'm going to introduce you the simulation part, and I shortly go back to ComposicaD. So I have the same model here open, the one Mike showed you. Well, you can see the geometry here, and also the mesh overlaid on top of the geometry. Okay, and what Mike showed you about the export of data to ESAComp, I will repeat that one. So I select the ESAComp drop-down menu, and now that we do a structural simulation, and because the tank is symmetric, I just simulate the 1/2 to save some time in the computation. I could use the default parameters for the mesh, but I will change the, well, actually I will change the settings to the ones showed in the showed previously. So I will do the export. I will specify the folder for the different files, and here is the folder open. So basically what is red in ESAComp is 3 files produced by ComposicaD. 2 of them define the finite element mesh with shell elements and nodes, and the third one introduced the laminate data. Also, in this specific file, the materials are introduced, so you can cross-check that you have the same data used in ESAComp and in ComposicaD. Normally, when I work in ESAComp, I have a template file where I have introduced materials that have been used in the winding simulation, but now I'm starting from scratch, so I'm going to introduce these 2 T700 high-strength carbon fiber material systems. What I'm going to do is I use ESAComp search function, and I will search from the database materials with ID T700 from the data bank. And as a result of the search, there are some systems matching with the search criteria. And for example, the one that I'm going to use is the one at the bottom from Umeco. So to introduce, the data has been gathered from the Umeco structural materials sites. It's a UD system with a fiber volume content 56%, so sufficiently close to the one Mike used in the winding simulation. There are engineering constants and then nominal failure values that are going to be used in the simulation. These are the nominal values for the UD laminates, but I'm going to introduce another strength set here, which I'm going to use in the later phases of this demonstration. So I will import the material into the working project, and I will close this search function. So I have here the material system, and I will modify the data by introducing additional strength set called fatigue. Well, let's say that based on my knowledge, I think that 0.5% global strain level is a good approximation for a certain number of load cycles. So that's in a simple manner presents the fatigue limit for this material system. And now I have in addition to the nominal values, I have the fatigue values here based on the 0.5 strain level. Before performing the actual simulation, I will need to introduce or I have to give a material ID for the material system so that it matches with the material system of the process simulation. So I will go back to ComposicaD and then materials. Mike showed you this specification window. So in ComposicaD, material ID 1 is used for a hoop. So I will slightly modify this. I will define hoop and then define the actual material ID so that it matches. And then in the structural simulation for the helical layer, I will use the same structural mechanical properties as for the hoop layer. So I just duplicate this material system. Modify the name just to identify and give a proper ID. So when you repeat your analysis, the previous steps you don't have to redo. This is something that you can take from the template file. Now I'm going to the actual simulation. So I just read in the data from ComposicaD. I specify the file, and before launching the simulation, I can select failure criteria that is going to be used for the UD material system. There are different criteria available, but I start with the max strain criteria. I start the simulation, and it takes like 10 seconds to run the simulation, and now it shows you the half tank. So we just simulate one side of the tank due to the symmetry. RF indicates reserve factor for the laminate, so it takes into account all the layers of the element. So it's like a piercing through the laminate, and then giving the indication what is the reserve factor according to the weakest ply of the laminate. The critical layer information can be seen on top of the laminate. So, for example, in this region, it's the layer A. A stands for the layer that is introduced first in the laminate. It's aligned in -88 degrees. So from that information we can judge that it's a hoop layer. Failure mode. In this region, for example, it's 2T. T stands for tensile failure, and 2 stands for the principal direction 2 of that specific critical layer. This information naturally depends on the selected failure criteria. Now we have selected the max strain criteria. Other result items, I will pick, for example, global strains. These are the global strains in the axial direction of the tank. So in the dome, it goes to the meridian direction at the inner surface of the tank, and the strains are in percents. Strains in the hoop direction now presented. I will take a view from dome direction, and now I will plot the in-plane shear I will a little bit scale, or actually quite a lot scale, the deformation. And you can see that how the tank distorts. So because the laminate structure is not symmetric, there's a bending moment in the dome region, and therefore the tank shears. One can do a point-wise analysis, so that means that I can pick elements from the model and study locally, for example, strains either in the local coordinate system or global system. So this one is for that point here, the next one. And then so on. So here you can see the different layer orientations and for example the layer that is in 14.3 direction at this region, it's heading to the point where it turns to the opposite direction, and the orientation has increased to 21.4. So one can do this kind of local studies. Back to this reserve factor, and this is something interesting region here. Why the reserve factor is lower at this region, and the mesh is rather coarse. So I decided to go to make another design loop with different mesh parameters. So I can go back to ComposicaD. I will go to the actual project and the mandrel data. So here was the original mesh and original length. For the second round simulation, I will shorten the tank. It doesn't influence on the results at the region where I'm now focusing. I will slightly change the mesh parameters. And the paths are recalculated, and I will export the data to ESAComp tailstock end only, and I have the updated data in my demo folder. Basically, I could rerun now the model, but I will do one more modification before rerunning the simulation. So I will go to the options, and I will now activate the fatigue values for the failure analysis. Previous analysis was made with the nominal values, but now this one with fatigue values. And I will repeat the analysis, and again it's something like 10-15 seconds calculation time, so it's really responsive. You can do a lot of what if studies, like if you see something, you want to try something, you go back to ComposicaD, make the modification, and then export the data back to ESAComp and then rerun. So now the mesh is different. Still there's some oscillation of the reserve factor at this region, and what I'm going to use, I will make a point-wise analysis at this region. By far, the failure analysis has been made only using in-plane failure criteria, but by experience, you may know that the typical region where the tank fails is this one. So let's take a look at this region more closely with the local analysis. And the strains, there's nothing exceptional. They are pretty close to the fatigue limit that I have used. But I will take now the stresses, and more specifically I will take a out of plane shear stress. So it's moderate in this region, 15 megapascals. Let's study the neighbors, or better. Actually, there's a better thing to look at the result item QX. It indicates out of plane stress resultant. So previously I showed you the out of plane stress distribution. This QX is like one item that shows the resultant of all the layers. So this gives you a nice overview where you have a oscillation of the result items. So in this region, QX has a high peak, and I will go to peak element from that region. And I study locally that one, and it's over 40 MPa. Actually, that wasn't straightforward to find that critical region from the model. So I will go once more back, and I will change the analysis options so that also the out of plane is considered. One possible way is to select max stress 3D failure criteria and repeat the analysis. And waiting the results. And now we have a clear indication that this region is a potential location for failure due to the high out-of-plane shear stresses. So potentially these high out-of-plane shear stresses induce delamination, and delamination increases, and that makes the tank to fail during the cyclic loading. So this QX was quite good result item to reveal that there is some change in the structure at this region. Other result items like NX indicates the stress resultant in the in-plane direction. So these are quite useful to see how the structure will change the state from one to another, from moving to the tank part to the dome. We have also capabilities like the data can be visualized in numerical formats, it can be exported to Excel, for example, and then the data can be processed in Excel if you find that good way of working. I will actually modify these semicolons to comma and open that in Excel and show you the QX how it makes high peak at the transition zone where the cylindrical shell part ends, and we move to the dome. Okay, that was my part of the presentation, and then I would like to conclude, summarize that this package of ComposicaD and ESAComp, basically it combines all aspects of the product development of pressure vessels, since manufacturing and the shape are considered on ComposicaD side. Also materials are also included in ESAComp, and the actual function is verified and simulated in ESAComp. So our approach is that you design something in the ComposicaD and then see that you can actually first make it and then see if it's feasible. I demonstrated that the tool is really responsive, and therefore it's a really design tool. You can make a efficient what-if studies. It's cost-effective and still it doesn't trade off from the accuracy, so it's in the same level as the commercial FE tools. Only that less effort is needed in the design work and in training of the tools. Software development is always like a continuous process, and certainly there are things that we have in mind and want to develop. But at the moment, it's really a major tool for the industry. I would like to thank you from my side, and now we open the part for questions. Okay, we now gather the questions that come in, and we will provide you answers personally. So don't hesitate to contact us and then send us emails. We will answer you promptly. We will provide the recordings of this presentation later available. So if your colleagues want to check, or if there was something you want to recheck, please have a look on the recordings. There's a question about the pricing, and then also we can give you a more specific answer for that one via email. But generally it's like if you have a cylindrical shell module of ESAComp, then this is included in that one. About the BOSS, that's one of the things we would like to introduce, and I'm not sure I cannot because I'm not managing this event, I cannot see the participants, but if Mike is still on the line, we have discussed with Mike that it would be a good approach. There would be some simple library of bosses available at ComposicaD site, and then one basically would select the boss from the library, and then that would be included in the FE simulation. So that's the proposed approach.
This is Mike. I'm still here. Hopefully you can hear me. That's the direction that we're moving in ComposicaD is to include those non-composite features, so the metallic bosses or end pieces, and then also the liners, if either metallic or plastic. Currently that's not being done, but that's the direction we're moving. Hopefully by next year we'll have that ability in ComposicaD.
There's a question about tutorials, and actually the version that is our latest release, official release of ESAComp, that is available with that release, tutorials are included. So there is a description of the workflow of so if you have ESAComp available under the documents folder, you will find the description of them. And please contact us if you have any further questions. We are happy to help you. And otherwise, if there are no questions, I'm going to close this meeting and webinar. And again, I will thank you for your attention, and have a nice day or evening. Bye-bye.
Thank you.